Ara and all the organizers for the invitation, for the opportunity to be back here at the IIP. It's a wonderful place. I don't say I miss the old villa, but it was also nice, a nice setting. I never used the swimming pool there, so I like it here better. So so as you notice, there will be two talks about related, a common theme. Let me put it this way. And the idea that I want to present some work we've been developing in the past 10 years or so, try to characterize this, what I call this fluctuation phenomenon in complex systems in a way that I'll make it more precise. So the way I organized the talk was in the spirit that was mentioned earlier today, a very general introduction, very basic, on what I call statistical mechanics of simple systems, essentially Gibbs formulation of the canonical distribution, basically to highlight what it aims to accomplish there. And then we want to move from there to describe other systems that cannot be described within the same framework. And that's what I call this hierarchical complex systems. And then you have to extend the formalism to include these others, if you want, aspects of this fluctuation phenomenon. But I will concentrate particularly in an application to turbulence, not turbulence per se, but turbulence would be my prototypical model where this kind of phenomena are observed, measured, and hopefully described. So that's will be our guiding problem. But of course, it has many applications, as you see. I'll mention just one more in this talk. Then Antonio Macedo will speak more about other applications to other systems. So as I said, this is work that we have been developing in the past 10 years or so. And today, I have chosen to talk particularly focus on this more recent work. It's a more general description of this, as I said, theoretical framework for this kind of problems. So as a way of introduction, let's briefly recall, of course, the canonical ensemble, or the canonical distribution, where you have a system, that's my small system here, which is in equilibrium, thermal equilibrium with a larger system, as we usually think as the heat reservoir with a given temperature. And of course, the question is what the probability of selecting a particular state, say characterized by these variables, from this system. Of course, we know that this is given by the Gibbs distribution, z of t, so exponential to the minus energy or Hamiltonian. This is the parameter that characterizes the equilibrium. That's important for us, of course. And this is the partition function. But notice that we all know that the notion of equilibrium in this context is independent of size. So it doesn't really matter what's the size of your system as long as it's big, and this one is even bigger, so that this energy fluctuation does not alter the temperature, say, of the larger system. So that's what we are in. This is the kind of equilibrium that I call simple system for a particular reason that I'm following Gibbs. And I like to quote from his book, just to set the context here, when he says that, I don't think maybe you cannot read from there, so I'll read for you. Particularly, he says that when the system consists of parts with separate energies, the laws of the distribution in phase separate parts are of the same nature. So, which means in my previous slide, so the distribution is the same both for the smaller system as for the larger system. So there's no dependence on the size of the system. And then he goes on that there's the property which enormously simplifies the discussion. So, and further he says, or before actually, he said that the distribution, this exponential distribution, seems to represent the most simple case conceivable. So that's the idea when you have the separation in energy and the property, of course, that your systems are independent. Of course, there are many systems in nature where the Gibbs distribution does not apply, and that's why I want to focus on turbulence, which is a very, very interesting and complex system, as I think we all agree. So suppose you have a jet that's injected here. So you have a regime which is called a laminar flow. So the velocity field is rather smooth at the beginning, and then you see some instability developing, and then you see a very complex pattern here. So in this turbulent region here, the velocity field is rather fluctuates rather widely, both in time and space. That is to say, if you put a velocity probe here at some point, and you record the velocity from time to time as a time series, and you look at the increment from one time to the next, that's the typical sign that you record. So it's a very fluctuating, seemingly random signal time series. So in that I mean is what you measure is just technical point is the longitudinal velocity increment along the that was in time. Then I said, if you also measure the velocity increment in space, so I was jumping ahead. So now you put a probe between 2 points, and you measure the velocity at the 2 points, subtract one from the other, and see the increment between two nearby points, and you project along the direction, so it's the longitudinal velocity increment. And you would see a similar behavior, but it's more interesting. So the main question of this project, and many people work on similar problems, is to describe the statistical nature of this fluctuation, right? So, and if you just do a simple histogram of signal like this, then something quite interesting happens. So if you have 2 points, now let's concentrate on the time, the velocity increment between two nearby points. If they are well apart from one another, then of course the velocity fluctuation at each point is dependent, and you would expect a Gaussian behavior, which is down here. So this is a semi-log, so it's a log linear scale. So the scale, a Gaussian would be just an inverse parabola. So you see Gaussian, but as you come close to one another, so it's short scale, the fluctuations deviate quite heavily from the Gaussian distribution. So this gives the origin to the heavy tails. So that's what I wanted to describe. Can you develop a setting, a theoretical framework when you can explain like a dynamical origin of the so-called intermittence, when the velocity fluctuation distribution is size dependent. So that idea that my equilibrium distribution now becomes size dependent. So it depends on the scale with which you make the measurement. So that's the goal. So which means that I'm forced to take into account the idea that I have a multiscale phenomenon. Multiscale dynamics, turbulence, maybe is one of the best examples of that, in the sense that the typical cartoon view of a turbulent flow is that you have to inject energy at large scale to form these large edges, and then they break into smaller edges, and then they break into even smaller edges, and so on and so forth, to have an energy cascade from large to small scales. So you can even see if you have large and then smaller fluctuations. Yeah. These will be three-dimensional. Most of the data that I will present will be three-dimensional, but you'll see the implications for two-dimensional, because you have both cases. In principle, it has to. So the question has to do with the order of this cascade. So here's the three-dimensional view, and you inject energy at large scale, and they break into smaller and smaller edges. You have a cascade of energy. So the kinetic energy is cascading from larger to smaller scale until it's dissipated by heat at the viscous scale. In two dimensions, the opposite, but we can contemplate both, I hope. So what I want to do now is to use this picture that I have to take into account the different scales. So within my, what they call my Now, global equilibrium. And the way we do this pictorially is I will enlarge that cartoon that I had before for the canonical distribution. So here's my system. So that's to give the idea that I'm making measurements that are given either time or length or both scales. And that the system, because the system has, I said here, several characteristics, scales, time and length scale. I have to say n. I have to take that into account in some way. So that's an effective way that we are proposing to take those multiple scales into account. So now the idea is that the system is in contact with a reservoir, but which temperature, which describes the effective degree of freedom of this larger system, now can fluctuate. So it's no longer constant. It fluctuates and interacts with another reservoir of a larger scale, which also has a fluctuating temperature. So you have this idea of a nested set of reservoirs, each of them described by its own fluctuating temperature. What we want to consider is we have a global equilibrium in this sense. So on average, each of those quantities have the same average. So that's our definition of global equilibrium. So how can this happen? At least I can give you, time average. Yeah. So there's no space here, so it's time average. Just to give you an idea of how this kind of, that's what I call this complex behavior, fluctuating behavior. If you look at turbulence as a guiding when this kind of situation can happen, so you need to somehow generate intermittence when this, if you want intermediate or local temperature fluctuate. So inject energy at some level, and eventually disappear at some other level. But on average, you have this cascade without dissipation, so whatever you put in, you get out, and then you reach this equilibrium. So, so that's the idea. Now, question. But then you have to, of course, put additional hypotheses, and one of them that you have separation of time scale. The smaller, the faster. So the dynamics here is very fast. This is a bit slower than this one. This is even slower than that one, and so on and so forth. So which means that if this one, the dynamics is very fast compared to this one, before this temperature of the innermost, I call reservoir, has time to change, the system has already equilibrated or quasi-equilibrated to your usual, to the standard Gibbs canonical Boltzmann-Gibbs distribution. So that's the idea. But now we consider a conditional distribution of states, conditioned to the value of your local temperature or your inverse local temperature, which now fluctuating. So that's the first part. Now, and then because your temperature is fluctuating, the marginal distribution have to average sum over all possible value of your temperature from 0 to infinity, weighted by some distribution of your temperature, your local temperature. So now temperature becomes a random variable. And this is just a compounding of distribution. Some people in physics call it superstatistics, but it's just a compounding, superposition of your local equilibrium distribution. There are some examples that you can consider. I just mentioned that this could be the Gibbs distribution. The work I'm going to show concentrates on a Gaussian distribution for velocity fluctuation in a turbulent flow. So you have so that your temperature is some measure of the average energy, or actually the average energy flow in your system. But now it fluctuates, and you have to do the same sort of average. And there are other examples I will briefly mention. Maybe if you have some reason to believe that your sort of local distribution, say it's a Levy distribution, you can do the same kind of procedure. that's what I'm going to do now. That's the main part of the work, is to compute or derive a dynamical system, a dynamical model from which, based on some very few basic assumptions, from which I can compute this distribution. So that's the probability density of the temperature at the innermost. Yeah. So this is fluctuating. So it's a random variable. It's coming, if you want to physically. Physically, it's coming from, well, depends on what you mean. You can derive models for it. And physically, it has to do with the kinetic energy. If I can just go back. You cannot measure it directly. But it has to do, if you are measuring at a small scale, it has to do with the environment, some typical size of the edges that your system is probing. So it's this. You see it's universal function. There are two universality classes. So that's important. The main point is to compute based on some an effective model, how to compute the possible dynamics of such a temperature. The origin, the physical origin, is precisely this complex dynamics, multiple scales, this interactions between different scales that give rise into this. So what I'm trying to say naively is that the particle that you see, that you follow in one of those particles, experience a different environment at different moments in space and time. So that's the idea. So it's different from, say, ideal gas, when you always see the same environment, which is essentially the walls or your reservoir. No, it's a more complex structure. So, of course, I cannot take into account, I cannot compute that from the Navier-Stokes or from a microscopic model, but I can compute from a more, you see, a stochastic model. That's what I'm going to. So that's the main point. So let's see if I can convince her that we can construct a general framework from which to deduce, or to compute, actually, this distribution. That's precisely what we wanted. So, of course, I wanted to take into account this idea of a cascade model, that there's local interactions between scales that are nearby, that are comparable in size. So a small system does not see directly the interaction of the larger scale, but only at the scale similar, or larger but similar. So this idea of a cascade or local interaction will be represented. So of course, it's I want to write down a Langevin or a stochastic differential equation for this quantity at each characteristic level of your, or at each level of your cascade, of each characteristic level of your dynamics. Oh, another question, another point. I don't know how many of those levels there are. Right? So I have to infer from the data. I'll show you how to do that. Right? I don't know how many, in principle, for a system as complex as turbulence, I don't know beforehand how many degrees or how many scales in my cascade I should consider. But there's a way that we can compute from the data. But for that, I need to develop a theory that can incorporate this multiscale dynamics. So the idea is then I want to write down a stochastic model for my cascade. It has to take into account this hierarchy of length scales. So that's why I say that the temperature, the fluctuation, the temperature at a given level depends only on its own level, the fluctuation, and the level nearby, the one above. So that's the statement of a cascade. So they interact only through a nearby scale. Oops, sorry, that's already the full model. The same for this, those are the deterministic term. So this is essentially the idea that if they are at different temperature, they'll try to equilibrate and reach the same constant temperature. But of course, you have intermittence, you have fluctuations, you have to add some noise, and you have to add a multiplicative noise, whose amplitude also depends only at most at the two nearby scales. And W is a Wiener process, so they consider independent Wiener process through this cascade. And here some, if you just impose some very basic principle, so it, of course, should be invariance by a change of scale units of your temperature, which is a measure of energy or average energy. So it should be a homogeneous function of degree 1. Same for the noise term. And furthermore, I want to ensure that the temperature is a positive quantity. So I assume it's a continuous process, now it's a diffusion process. So 0 should be a non-crossing boundary. So whenever this process reaches 0, it has to bounce back to a positive number. And you ensure that if this multiplicative noise is 0, when the temperatures are 0, basically when Ti is 0, and if this quantity is positive, so when Ti is 0, then this will be a positive, so it gets a kickback to the positive. So it never crosses the real line through the negative. And the simplest way to guarantee this two property is if you put your multiplicative noise, which is just a power law of Ti and of Ti minus 1. So, and the S is a scale exponent between 0 and 1. So you satisfy this property here, and it's the very general multiplicative noise. So I want to now explore the consequences of this. I still have to, of course, prescribe what are the determinist coupling. The basic term is you just have a Newton's law of cooling. So the rate of change of temperature is proportional to the gradient, or to the difference between the two. But I wanted to be a bit more general to include other facts that I'll try to explain later. So next term, I will write this way. So here, it's important. Note, I learned that I have to write down notation. So from now on, because I have turbulence in mind, just because it's easy, at least for me to explain, because of the kind of questions that Ara has already raised, I use the notation epsilon I because, and it's not energy, this temperature is kind of a measure of some mean energy, but in turbulence, I'll replace this by this symbol, and in turbulence, as you saw in the Cascade cartoon, is rather the rate of change of transfer of energy between scales. So it has you can think of energy. So that's why I'm changing the symbol. But in my brief, so just make sure that there's no confusion. So in this cartoon, this is temperature, but I'll just replace this with epsilon n, which is some measure of energy, typical energy, if you will, on that level, on that scale. Because as someone else said, that's the latest paper, and they use now this notation. So let me remind you that here is the noise term. So here's the noise, the multiplicative noise, epsilon I to the S, epsilon I minus 1 to the 1 minus S. So it has the prop that I mentioned before. In the determinist term, usually the simplest one is not, of course, it's not this one. Is, as you see, I would anticipate here, there's only two universality classes, as you see. The first one, we should move. If S is 1, I'll just write it here. D epsilon I is minus gamma 1 epsilon I. And here I'm making also gamma to 0, okay? So, so if you, sorry, I'm making, no, I'm this one, huh? Okay. So, yes. So, right opposite, sorry. Because I'm writing the reverse order. So, S is 1, so this term just have a constant, so this should be gamma 2, not mistaken. And gamma 1 is 0. Right? So that's the simplest way. That's how we started. This is 2010. And then you can see this is just what we call the stochastic Newton's law of cooling. And if you take the other class, now it's the opposite, let's see. S is 1/2, so this term is no longer present. Then you get minus gamma 1. And here you change the amplitude of the noise. And here I chose gamma 2 0. You see why. And this is a more recent work. That's with Antonio Murillo. Yeah. That's I'm trying to convince you that I have to look at the ratio of energy, how the energy flows. We have yeah.
So do you have such conservation in your model or not? So how you?
Well, in this, the simplest version, you do have energy conservation in that global sense. So if you look here, in any case, you have an epsilon 0 at the first level of your cascade. So this, when time goes to infinite, you always have equilibration. Okay, so on average, you always have conservation. Okay? But of course, from this one, we could distinguish between the two, and I cannot say that one is direct or the other inverse. But then I want to add a little bit of dissipation. So that's this recent work is if you now add a little extra piece here, or a little extra piece there, and it can only be in this way. That's the combined. So we have written a combined system, a unified, we call model for this intermittence phenomenon. And if you add then a little extra and a little extra bit there, then you see that in this case you have an inverse cascade, at least in my interpretation, and this you have a direct cascade. And I'll try to justify why. So that's what I'm trying to. Yeah. We no, they are, well, only in the sense that maybe it's written here, not yet, but of course, the distribution, the stationary distribution depends on the ratio between the two. So we call it beta I is 2 gamma I kappa square. Right, so there's one parameter that characterizes the distribution. So let me carry on now. Some calculation. I can solve, of course, then take the general model, compute, solve the Fokker-Planck equation for the stationary regime, and lo and behold, you find that remember I said there's a large time separation of time scale, large separation. So what you have to do here, you hold this guy, say, fixed, and solve for the distribution for so you hold the immediate, if you want, reservoir, you keep that fixed, and solve for the probability distribution for this guy in the stationary regime. You solve your Fokker-Planck equation, and you find this condition distribution. It's an easy calculation. And it has a nice, I don't know if you are familiar with this, but it's a so-called generalized inverse Gaussian distribution. Interpolates between a gamma and an inverse gamma. So it's so this case, if you just solve for this one, you get a gamma, inverse gamma distribution for this guy, and this is a gamma, and the gig is a combined exponential. So that has a nice unifying property. But now I want to find this one, because I'm measuring this system. I want to know what's the distribution of the innermost temperature, and you have to average over all intermediate scales. You do this multiple integral from 1 to n minus 1. And the nice thing is, because I have these gigs, this exponential distribution, the way you do this integral is by introducing the Mellin transform. I don't want to go into the technical details here. But the important thing is that the Mellin transform, so defined, of a gig of generalized inverse Gaussian is a product of this K Bessel function. I forgot to point that. So here it's important that the normalizing factor of the gig distribution is a modified Bessel function. And now, if you use that the Mellin transform of a gig is a product, each gig is a product of kappas. Then you have n of those in the integral. So what you have to, it's easy to compute the Mellin transform of this distribution. And then you have to take the inverse Mellin transform, and then you have to work a little harder to get that, right? So, and the thing is that you have to define a new special function which generalize the Meyer-G function. If you are familiar with the G-Meyer, if you ever heard of it, the Meyer-G function is a function whose Mellin transform is essentially this part here, which is a product of gamma function with some parameters. So you have a list of parameters on the upper and the lower entries. And you can just, so it happens that the function I need is a generalization of this Meyer-G function when I replace the gamma function by a product of this modified Bessel function in an appropriate way. So we had to introduce a new function, which we call the R function. As I said, generalize the G function. It has inherits the same nice properties of the G function. And in particular, you can, it's related. So I've just, if you now go back to, that's the Mellin transform of my function. If you compare this with the general definition I gave you of the R function, I'm not going to that here, you conclude that the distribution, the probability density function of your innermost temperature or energy transfer rate is given by this new special function. But and the good thing is that now I have just one single distribution for this family, one parameter family of models. There's a parameter S that interpolates between these two, or more. The physically relevant models are for this two particular case that I have there. So just to try to justify why I call them, I call the, if I put a bit of the extra term here, the gamma 1 term, and here the gamma 2 term, this I call a inverse cascade, and I call this a direct cascade model, because if you compute the average energy, or energy flow, or energy transfer rate actually, at a given scale compared to the same arbitrary scale before, you get this limit, this value in the limit that gamma 2 here. Oops, sorry. Here, the limit that gamma 2 goes to 0. So you can see that the emergence at the lower scale is smaller than at the larger scale. Sorry. Sorry, I should have switched it off. So see, at the smaller energy, at the smaller scale, there is less energy than at the larger scale. So it means that as energy flows, some bit of dissipating throughout the scale. So in this sense, so this extra parameter is like taking into account some residual energy dissipation at the scale that's not yet at this limit. So in this sense, I call, so energy is going from higher to from larger to smaller scale. So in each level, there's less energy than, a bit less than in the level above. And if you do the same for the other model, it's the opposite. So in the smaller scale, there's a bit more energy than in the one above. So I think that energy, you can think of energy going from smaller to high scale. So it's in this sense, this specific sense, that I say that they can model, if you add this, it's a bit of dissipation within each level. Okay, so that's the general framework. So I want to now try to apply this to turbulence. So I'll show you some pictures. And so what I want to model then is the distribution of velocity increments in a turbulent flow. And particularly, I want to describe this asymmetry. As you know, that the probability the velocity increment distribution is skewed towards negative value, follows from the Kolmogorov 4/5 law, but it's not important for us here. I wanted to construct, or to obtain, rather, a distribution that has this property, where I can actually compute the tails in both sides. So if I want to get a skewed distribution, you can now make a compounding or a superposition of Gaussian, but with non-zero means. If you start with a composition of a symmetrical distribution, you get a symmetrical distribution. So it's a Gaussian, for the reason I explained before. But now the mean is also a random variable, and I take the simplest model when the mean is proportional to the variance. So it's a mean variance model. So, and if you do this, then this is a cartoon that shows that you do get a symmetrical distribution in this way. So, and then I restrict to what I call the cascade, direct cascade model, so it's the square root noise. I just told you that this is an R function. I have now to compound with the Gaussian. Here's my Gaussian distribution. The Gaussian can be written as a G. A G can be written as a R. So we have the integral of 2R function. There's a nice convolution theorem. The integral of a product of G functions is another G function. The same holds for this R function. In the end, you have an explicit analytic formula for this marginal distribution. And you can now do a saddle point calculation and show that it does indeed have asymmetric tails. See, there's an extract exponential from one side. And it's just it's dominated by exponential decay on the opposite side. So, and it's important to note that you only get extract exponential if n is larger than 1. So n is the number of scale I need to increase to consider in my model. And if n is 1, you only get exponential decays, some sort of semi-heavy. I'll skip the numerical details, how you compute. But you can compute given that's a DNS, so it's simulation. But we are actually analyzing some experimental data, but it's not ready yet. So this is some simulation data. I think I put it maybe in the next, oh, here. So it's a 1024 cube. Cube with 1024 points. The Reynolds number for this case is 433, the Taylor Reynolds number. And then you compute the parameters of the model. Oops, that's what I hope. And when you find your condition distribution, so the condition distribution, or maybe I should have to just say one final. But you have to find is this parameter here, that I call energy, is the variance in my model. So I actually have to generate a series of variance. My original time series, I divide in smaller blocks. In each block, I compute the variance, or variance estimate, and have a series of variance with which I can do this calculation, or this numerical analysis, rather. So this is the condition distribution, the velocity increment for a given epsilon n for these values, and you see that they nicely fit into a Gaussian. So that validates that. Now, that's another important piece that maybe I have to keep going back and forth, but maybe here's enough. So remember that my to get the marginal distribution, which is what I measure in the laboratory, from the theory, I need to compute this, and then do this integral, and then I get both of them written as an R function. But now, the fitting for the parameters, I can give you details more, is done on the distribution of the variance series. So I compute a series of variance estimate. That's the histogram of that auxiliary series, and I fit here with one of those R functions I showed you before, and I get two parameters. The symmetry parameter I had determined before, but that's the two parameters, alpha and beta. And now I just use these parameters in my theoretical formula for the velocity distribution. So there's no fit in here any longer. I just plot that function, and you see the agreement is very good. So it's a sort of nice self-consistency check that I fit what you call the background variable, or the background signal, the background series, and then after that, you plot the distribution of your signal. And you see this nice agreement. I keep pressing the wrong buttons. So the last, and you can do for higher, this is for higher Sisman, larger Reynolds number, you get the same very nice agreement. So I'll skip that. Just as a way of coming to the conclusions, I just want to brief mention a working in progress when you've been analyzed fluctuation in this graphene membrane, just a freestanding graphene membrane, some experiment done, I think in the States, with people, other collaboration. They just have a membrane, and they, with a microscope, a probe here, they measure the height of this membrane. So it's a height fluctuation, and if you take increments, you get a velocity fluctuation here. And they do a statistic, and they get some Cauchy distribution, which is a power law distribution. So what we want to do now, is I can now carry on with this analysis, but now what we call our local equilibrium in this particular case could be a Levy distribution. A Cauchy distribution is a Levy with the alpha parameter equals 2. So I can now do a compounding of Levy distribution, then I have to use one of those formulas for the distribution of the parameter of the Levy distribution. It's no longer variance, so it's more complicated, but you can do the calculation. Now you get the Fox age functions, and you compare with the data. So it's a preliminary analysis, but it's the same. See that the condition distribution is very close to my Levy for some alpha 1.78, so it's not 2. So this alpha equals 2 that they use in the paper. So you can we describe a much nice agreement for this model. But this We need to study more data, but that's just to give an idea that you can do this kind of description with non-Gaussian, more general distributions, and I think Antonio will describe more other applications. So in summary, what I tried to present to you was this unified description of fluctuation phenomena. I said classical, but I think Antonio will mention some application in quantum systems, and it can even be done in relativistic systems. That's also work in progress. And in all these cases, you have to take into account this multiscale dynamics, as I tried to explain very rapidly here. But the good thing is you always have an analytical expression, if in terms of this special function, that allows you to analyze the details. The features are quickly done. So you have a much robust and more powerful technology to analyze this kind of phenomenon in many systems. I presented only turbulence, but have analyzed, of course, turbulence in financial market. I said we are working on this hierarchical Levy distribution. I think Antonio is speaking in the next talk about this other system. We've been collaborating with some people to try to extend this to the so-called Maxner-Utner distribution, and perhaps other systems are also can also be studied. And with that, I thank you for your attention.